right, gang. Good to see you guys again. Today we're going to talk, since we're just about through derivatives for the year, we're going to talk real briefly about something called Lopatal's rule. And it's a really a cool thing. It applies derivatives and it takes it and it uses it towards something called, or uses it towards limits. So we are in 5.6, so Lopatal's. All right, so that's French. I'll say I don't speak French too terribly great. There's a little crazy little thing. I'm not really sure what that's called. One of you guys will have to tell me in class what that thing's actually called. Anyways, here's what Lopatal's rule says. It says, given the limit, and I'm going to have to come back to this here in a second. Suppose that f of x and g of x, so there's going to be a g of x in there, friends, are both differentiable on the open interval containing sum x equals a. Also suppose that the limit as x approaches a of f of x equals 0, and the limit as x approaches a for g of x equals 0, then Lopatal's rule states that, and I'll write that in there. So what does it state? First of all, let me add in some things here that I can't quite do here just with generic. So as the limit as x approaches a for f of x divided by g of x. Suppose that f of x and g of x are both differential. By the way, they're both differential, and they also are continuous. I want to keep always kind of reminding ourselves these things. And suppose that the limit of as x approaches a of f of x equals 0, and the limit of x approaches a of g of x equals 0. Lopatal's rule states that the limit, and by the way, this is only one form of Lopatal's. We'll get to the other one here in a second. Just going to start off, we're going to look at the two cases of Lopatal's rule, because again, it's really slick. It states that the limit of f of x over g of x at x equals 8 equals the same limit as f prime of x over g prime of x. And friends, this process can continue if we needed to. So I'm going to add a few little dots there. So what does this actually mean? So when we're using this thing called Lopatal's rule, what it's telling us then is if I'm given some sort of a limit, like the limit as x approaches 1 for the natural log of x over x minus 1. If I were to just plug this straight away in, I end up getting the natural log of 1 over 1 minus 1, which is 0 over 0. So notice I end up getting an indeterminate form. So the indeterminate form means that I can possibly do something. So before I can use Lopatal's rule, I have to first show that it's indeterminate. So, and now comes the setup. Okay, so I mean, if it was just on a multiple choice, you would just jump right into it. But if it's on a free response, which this will be on a free response, it's been on a free response the last 4 years. So you would expect to see a little bit of a setup here then. So then let f of x be natural log of x, and g of x. So we set it up. At these 2 points, or these 2 functions. So now we're going to go through and do the first part. So the first part said, is it differentiable? Okay, is it differentiable at A? So in this case, they will both be differentiable at A. So we're going to go ahead and write that. F of x and g of x are differentiable at A. So we're giving ourselves permission. We're kind of going through. And then next thing we got to do is we got to deal with the limits, because that was the second part. Do the limits equal 0? So the limit as x approaches A of the natural log of x, oops, not A, sorry about that. I should have used the value here. I should use 1, not A, sorry about that. There we go. So if I plug 1 into here, the natural log of 1 is 0. And if I plug 1 into the limit of g of x, that equals 0. So what we're doing is we did the setup. So we went ahead and defined both the numerator and the denominator as a function, determined that they were differentiable, or at least stated that they're differential, and then stated that the limit of the top and the bottom are both equal to 0. And then from there, we can get into Lopatal's rule. So then we can say, by Lopatal's rule, if I can figure out how to spell, there we go. So then by this Lopatal's rule, we can go through and state what we can do with this. But the key here, and this is the part, is I had to do some of the setup. If you jump right on into it and you get right into the problem without doing the setup, the College Board will dock you real heavily on a free response portion of the test. Again, on the multiple choice portion, they don't care. You're good to go. So I've already showed this is indeterminate. I've said that both the top and the bottom are differentiable, and they both give me a limit of 0. So now I can use Lopatal's rule, which says that the derivative over 1. And if I plug that in there, friends, I get 1 over 1 all over 1, which equals 1. So then I get myself a little therefore, and we'll go back and write it one more time to kind of close it all off here. This is Lopatal's rule. The biggest part about Lopatal's is you have to set it up. If you don't set it up first, by saying that they're differentiable and showing that they equal 0, you're not going to get the credit you should get into 0 on the FRQ portion of the AP test. You have to set it up. And again, multiple choice, don't worry about it. So let's have you guys try one of these. Okay, and remember your form. Form's important. Let's try this one. The limit as x approaches 0 of e to the x minus 1 all over sine of x. Cool thing about this is this little thing that we're dealing with here would have worked for every limit we did first semester. This Lopatal rule is cool. Just the only hard part about it is the setup. Anyways, why don't you go ahead and pause the video and let's see what you guys can do. All right, let's see what you guys did here. First up, you got to plug it in here. Is this indeterminate? If it's not indeterminate, then we just can go right on through. So if we plug it all in here, that equals 0 over 0. So it is indeterminate. So now we're going to go write our book. Let's let f of x be equal to e to the x minus 1. And let g of x equal sine of x. F of x and g of x are both differentiable at x equals 0. So we did the write-up, did the setup. Now we're going to go ahead and come down here and we got to show that the two limits, wrong color, actually equals 0. So the limit is x approaches 0 of f of x, that's e to the x minus 1. Plug that in there, I get 0. And I got to show that this by itself is also going to be equal to 0. So we're doing this setup here. All right, again, multiple choice. We're just going through. If I'm shorthanding it as a regular problem, I'm not doing this setup. But for the AP test, we've got to make sure we explain our reasoning. So my Lopatal's rule. So we've gone through, we've explained it all, and now we can go ahead and solve it. So e to the x minus 1 what some people like to do, and it's okay, what some people like to do is they actually like to go ahead and show that they're doing the derivative. I personally think if I was on the free response portion of the test, I would definitely take the second to make sure that I showed both these. For some of you guys, you might think, it's a waste of time. But when you come to the free response portion, you want to show the AP board, the College Board, your reasoning. So I actually think it's worth taking an extra step and adding that in there. Because all you're doing, even though we didn't do it in the last one, what you're doing here is you're basically saying, I know what Lopatal's is and I'm showing it. And the reality is I probably should have done it on the first one too. It's good to add that step in there before you jump right to the derivatives. Now notice, if this was still 0 over 0, it's not, but if this was still 0 over 0, I could go do the Lopatal's rule again. Lopatal's rule basically says, hey, you can keep going as many times you want to until you get to something that actually works. So if I plug my 0 into all of these here, I end up with 1 over 1, which is 1. All right, let's try another one here. And I'll go ahead and make sure that I add that derivative step in there. The biggest thing is the setup. You just want to make sure that you explain your reasoning all the way through. Don't just jump into it. And this is one that the College Board started using a couple of years ago, or use something similar to it. You have a couple problems on this on your homework like it too. It's kind of an interesting idea. Where they actually end up combining a whole bunch of things. I actually think it's kind of cool. All right, friends. So why don't you go ahead and pause the video, try this, see what you guys can deal with. All right, let's see how you did here. So now, first thing you'd want to do is you want to go through and show, first of all, that it is actually indeterminate form. And when the bounds are the same, our upper and lower bound here are the same. That means that it equals 0 itself. And down below, I'm going to have the natural log of 1, which is also going to be 0. So this is 0 over 0. It is indeterminate. It's very weird indeterminate, but it is indeterminate. So now we're going to do our setup. So let f of x be equal to so I can't make that 2 a little bit better down there. There we go. And that g of x be equal to the natural log of x minus 1. F of x and g of x are both differentiable at x equals 2. Yep. So now we go ahead and we show that each part of the limit is 0. So the limit as x approaches 2 if I plug this in here, and again, we've kind of already done that when you first show the indeterminate, but it's one of those things where we really want to make sure that we're doing our setup, getting our setup for Lopatals completely right. We want the College Board to be really happy with us here before we actually jump right out into it. And again, if we're on the multiple choice portion, we don't have to necessarily worry about the setup. We just jump right into it. Okay, so we set it all up. Now we can use Lopatals. So what we can do now, since we know that it's not going to work in and of itself, we end up with something that's indeterminate. And this is where actually it is really good to actually show that derivative step. So we're just going to make a habit of it, just always showing that. So we know that since this is 0 over 0, we've given ourselves permission to do Lopatals. So what we're going to do then is we're going to take the derivative of the top and of the bottom. And so this is where, if I'm doing a derivative of an integral, all of a sudden bells and whistles go off. That is our second fundamental theorem of calculus. So it kind of combines the two. It's kind of a cool idea. So we're showing the College Board what we're doing. We're doing the derivative of the top, and we're taking the derivative of the bottom. And when we do that, we do our second fundamental theorem of calculus on top, and we end up with, instead of 3t minus 1, we're going to get 3x minus 1. And instead of natural log of x minus 1, we're going to get 1 over the x minus 1. So we took both our derivatives. Now when we plug them in here, we're going to get 5 on top, and we're going to get 1 over 2 minus 1 here on the bottom. I should probably show that first. Which is 5 over 1, which is 5. So that's Lopatal's rule, at least the first part of it. The second part of Lopatal's rule says, hey, it also works if they both equal infinity. Or in this case, also negative infinity. So if they both equal infinity, that's still a form of indeterminate that's also going to work for us to be able to use Lopatal's rule. So let's see how that works. Let me just kind of erase some stuff here, magic eraser. Lopatal is a cool boy. All those limits we did back in chapter 1. Lopatals, once you know how to do a derivative, Lopatal just kind of cleans them all up, and we can just zoom right through them all. It will do every limit for us. Again, the only important thing, remember though, is that you have to show the setup for it. When you show the setup though, you are good. All right. So let's try one of these here. What would that look like? Say I give you a function like limit as x approaches infinity. And we'll go x squared over e to the x. And if I plug in my infinity in here, I end up with infinity squared, which is infinity. E to the infinity is infinity. It's indeterminate, can't be done. So we're going to use our Lopatals. Just like before, though, I have to make sure that I go ahead and set it up. Let f of x be equal to x squared and g of x be equal to e to the x. Both f of x and g of x are differentiable at infinity. So we get it all set up here. Now we're going to show our work over here. Again, we've kind of already done it, but we want to make sure that we prove it. And we end up with the limit as x approaches infinity of x squared, that's infinity. And we're We can do it for the other one as well. And again, we've already done that by showing that it was indeterminate, but we have to just get the setup right. Make all our friends happy when we explain what we're doing. Now we can use Lopatals. All right, so by Lopatal's rule, we can go through and say we end up with the derivative of both top and bottom. So we're showing that we're using Lopatals right now. And when we do that, we end up with two x over e to the x. Well, friends, I'm still infinity over infinity. So guess what? Do it again. Lopatals, I can keep doing it again until I end up with something that is friendly. So it didn't work the first time. I can compare again. Actually, I probably should. So let me do that. I already said that e to the x is f g to the x, so I don't have to worry about that. But I am going to have to go ahead and I'll let h of x be 2 to the x. Is differentiable at infinity. So again, we're just making another comparison here that, hey, wait a second. Got to do it one more time. I'm going to do my setup real quick. I'm going to give myself permission to go and do a derivative one more time. So what is that? 2x? There we are. Well, that equals infinity. And now we've given ourselves permission to use Lopatals one more time. And again, if you're on the multiple choice, you're obviously not doing the setup. You're just going to kind of zoom through here fairly quickly. But on the free response, we need to give ourselves permission on everything. I think on a couple of ones before, I forgot to rewrite the original limit, the value, now that I'm playing it back in my head. So I want to make sure we do that too. I'll do that here on this one. So the derivative of 2 to the x and the derivative of e to the x we still end up with the limit of 2 over e to the x, which is going to be 2 over infinity, and that is 0. Therefore, the limit would be equal to 0. Lopatals is really cool. It's pretty slick. For the longest time, we didn't teach Lopatals in the AB. It wasn't part of it. However, we all still taught it to everybody because it works out so slick. And then the College Board decided, we probably should formalize this since everybody's going to use it. All right, friends, let's have you guys try one more, and then we will call it a day. The limit as x approaches infinity of e to the 3x all over root x. All right, go and pause the video and take a shot at it and see what you guys can do. All right, let's see here. So that would have been infinity over infinity, so it's indeterminate. We're going to go and do our setup here. Let f of x be equal to e to the 3x and g of x equal to the square root of x, or x to the 1/2 power. Both f of x and g of x are differentiable at infinity. So we've given ourselves permission just about. Got to prove these real quick, or at least show these. The limit as x approaches infinity of e to the 3x, that would be infinity. And we do it again for the square root of x, which is just x to the 1/2. Which would be infinity. So by Lopatal's rule, I don't need too much room on this one because I got a feeling this one's going to work the first time for me. So we end up with e to the 3x over x to the 1/2. And now we can use Lopatal's rule. I can take the derivative of the top and of the bottom. You can kind of see why we couldn't learn L'Hopital's before. You kind of need to know your derivatives before you can actually do L'Hopital. So there's some of you guys are going, why didn't we just learn this at the beginning of the year? Well, you can't do it until you actually know how to take a derivative. So we take our derivatives now. And we end with 3 times e to the 3x all over 1/2 x to the negative 1/2. And I'm going to just move that x to the negative 1/2 down to the bottom, or up to the top. I'm not really sure why I did that there. And we end up with 3 e to the 3x times x to the 1/2 over 1/2. And friends, it still equals It's not infinity over infinity this time. This does equal infinity. Therefore, there's going to be no limit. But the limit doesn't exist. But let's set that up real quick. Therefore, e to the 3x over root x equals infinity. And since it is unbounded, we can say furthermore, the limit doesn't exist. Channel your inner mean girl. We haven't done that for a while. Does not exist. All right, friends. Well, that's Lopatal's rule. It's kind of a slick little thing. We'll see you guys in class tomorrow, and we will talk a little bit more about this. All right, take care.